Hi, my name is Gianmarco Iodice. I'm leading the software engineering team at ARM for Generative AI. And today I'm here in Milan to talk about Generative AI at the edge, in particular to explore the real possibilities of GenAI on edge devices. In this workshop, we're gonna learn how to deploy large language models, a smart home assistant, and an audio generation application. So we saw the per channel and per block. Why it is? Because you're gonna see these in the frameworks. We're gonna talk about it today. There are many frameworks. These are crucial concepts. I'm just just summarizing what I have just said, so we are waiting for the people. There is also another concept that you should be aware of, which is the dynamic quantization versus static quantization. If you are from a tiny ML space or edge AI space, this is a huge difference. This is something that it's happening, in particular for generative AI, and might be also very relevant for other use cases with other networks as well. So let me double check. The other people, no, perfect. I think we can resume from this. We have our LLM, we have our matrix multiplication. As I said, left-hand side, right-hand side are the two inputs. The right-hand side, the weights, constant. What does it mean? If it is constant, I can quantize it ahead of time. So before the deployment, I can quantize it to maybe integer 4 per block or per channel. The activations, here the activations are not constant. It's something that changes because of the prompt, because it is the input for other layers. So one approach that we have seen in the past, in particular for edge AI deployment, and I'm not talking about generative AI, was static quantization. Who is familiar with the static quantization with integer 8? For instance, with TensorFlow Lite for microcontrollers. Anyone familiar with that? Okay. What did we have there? We trained a model in floating point, right? Then we use the TF-Lite converter, and we provided what? The representative data set. It was a portion of the data set to estimate the distribution of the values for this static quantization. In short, what scale and offset I should use for all the inputs. Why this? Well, because the input is dynamic, is not something that, in order to calculate the scale and offset, you need to know the statistical distribution to minimize the error between the floating point and integer conversion. Well, for generative AI, first of all, the data set is not that small. Second, no one is keen to share the data set. So there is one problem here. Therefore, it was invented an alternative solution, the dynamic quantization. So rather than have a static quantization, the model has a floating point activation, then we dynamically quantize to integer 8, for instance, at runtime. How do we do it? Check the metrics, we extract the statistical information like the min and max of the values stored in the tensor, then we can estimate or we can calculate the scale and offset to map my floating point to integer 8. This is very, very common. This is what you see in many LLMs right now, in many different frameworks. So this is, in short, the data types that we have mentioned earlier. So the integer 4 is very popular. It's providing very good accuracy. We have seen very good accuracy also for 500 million models. Below that, it depends whether you want to use integer 8, because anyway, the model is large, but not that large anymore. Integer 2 we have seen this happening, but in particular in the mixed precision fashion, okay? What does it mean? It means that some layers are much more important than others. So probably for these layers, we use integer 4, and the integer 2 for the remaining ones. This is actually quite important. Integer 1 is a promising area, but as I mentioned at the beginning, this is actually not integer 1, is the in 1 point something. But it is quite powerful when the model is very large, okay? But it's still a very, very promising. What you need for that? You either need or the hardware that supports these data types, but if you don't have the hardware, doesn't mean that you cannot use these data types. What you need is the software programmability. Okay, software programmability, if you don't have the hardware, is the key for that. I mean, if you're using a CPU, having these data types is quite straightforward. What open source frameworks can we use? Who is familiar with, okay, I heard TensorFlow for microcontrollers, but LiteRT, who is familiar with LiteRT? Good, good. LiteRT is basically what we had in the past. TensorFlow Lite is becoming LiteRT. So Executorch. Llama.cpp. Whisper.cpp. MNN. Okay, good. On the next runtime, how many open source frameworks do we have? This is great. I mean, it's great to have all these frameworks. So, and why this is great? You can say, well, I have so many frameworks, which one should I use it, right? So that's a very good observation, but it's actually great because all of these frameworks, they bring a strength, okay? There are so many LLMs, and what I'm going to do, this is actually something that I hope you can bring it maybe at home to try to play with, because there are so many LLMs, but there are also so many frameworks, and each framework has a specific, some specific capabilities, okay? Are all good, very good. Some for specific models, some for specific use cases, but depending on what you want to achieve, you can also do mix and match. So Executorch, I start with that because it has the seamless conversion from PyTorch model. It's part of the PyTorch family. So it has native support for dynamic shapes. Dynamic shape is something very important for generative AI. It wasn't a big thing for TinyML or Edge AI with convolutional networks, because what happened with TinyML and Edge AI for images, we knew the image resolution at the very beginning. So there wasn't a necessity for dynamic shape. For generative AI, the input is the prompt. How long is the prompt? Well, it depends. I don't know. So it depends on what the user is going to write. Okay? Dynamic shape, because the input is not fixed. And Executorch provides the native support. It's optimized for the Llama model. So if you're targeting Llama from the Meta family, so the Llama models, the Executorch framework is absolutely the best for performance and from a deployability perspective. They also have an interesting support for per channel and per block quantization, we mentioned earlier, right? Why this? Because you have the model in floating point, and through the Executorch converter, you can specify how you want to convert this with the PTQ approach. You can also, and this is very cool, specify which layer you want to quantize with per channel, maybe some layers with per block, maybe some layers with integer 4, some layers with integer 8. Mixed data type precision. This is absolutely very important. Another very crucial framework is LiteRT, and we're going to see all of these today, more or less. Very performant for convolution-based models. You have seen for edge AI use cases in most of the time. It has support for per channel integer 4 and integer 8. At the moment, no per block quantization. It has great performance for Gemma. Okay, if you're playing with Gemma models, this is the framework to consider. This is great performance, and trust me, there's nothing that actually can beat this. And we enter llama.cpp. I guess you are familiar with also llama.cpp. Very popular among the open source community. It's very easy to use. Is probably the only framework that supports a huge number of LLMs. Okay, it can support so many. But it's solely focused on LLMs and multimodal language models. So if you have a convolution neural networks, this is something not supported. Okay. The other thing is it supports per block quantization, no per channel. And here we mentioned about the performance, right? Per channel, something that we have in Light13 Executorch that we don't have in llama.cpp. And the block size is fixed to 32 values, if I recall correctly. What else? On an X runtime, high performant, very high performant for convolution-based models, and this is ideal if you have an on an X model. So the models that you find on, for instance, on Hugging Face can be in PyTorch format, but also can be in on an X format. Well, if you have it on an X format, probably the best place is on an X runtime. I need to. Yeah, forgot to mention. If you have a Phi model, another very popular LLM, this is the framework to consider. This we have already done it. So this is the first. What is? Doesn't work. Okay. So this is the first of the 3 use cases we're gonna see it. We're not going to run anything because we only have 40 minutes, more or less. But I will provide some instructions on how you can do it at home that might be relevant if you want to play with Llama 3. The only use case we're gonna see maybe live is the audio gen because it is very straightforward. So for Executorch, if you never use Executorch, one suggested link is this from ARM. It basically has a tutorial that explains how to deploy the Llama 3.2 1B. And in the tutorial, there is also the explanation on how to quantize the model. Okay, crucial. Based on one meta wrote in the technical document for Llama 3.2, almost all layers are in integer 4 format with per block quantization with group size of 32, so block size is equal to 32. But there is also the integer 8 per channel quantization, mixed data type precision, for some crucial layers, which are the classifier at the end, and also the embedding at the end. So at the beginning and end of the network, we use the integer 8 to basically minimize the accuracy loss. What I can tell you is that this use case can run everywhere. So if you're targeting the CPU, I think you just need 4 gigabytes of RAM to be safe, but 1B can also run on 3 gigabytes, more or less. It can run on Linux, Android, macOS, which means that you can run on your laptop, maybe on your Raspberry Pi, if you have one. 1B is quite good. What kind of tokens per second do you expect from a 1B? On a mobile phone, we were talking about 40 tokens per second, just to give you some numbers, which is quite a lot. If you consider that the AI can read at a speed of, 10 words per second, more or less, 40 tokens, which is roughly 30 words, 30 words, more or less, it's more than enough. Where can you use Llama 3.2? 1B. This is good for general chat. It's very good for summarization as well. And it's also very good for being fine-tuned as well. So you can adapt the Llama 3.2 to perform other tasks. On the Llama 3.2 official website, there is also a document that explains how to fine-tune it for other things. You can fine-tune it maybe to perform a different task, okay? As we mentioned, as we talked earlier. But given the size, this is absolutely quite good. Are you all familiar with cross-compilation, by the way? I believe so, right? Because for Edge AI, the cross-compilation is, well, we need to know it, right? So is the device where we're doing the deployment is different from the device where we are building the application, the host platform. So this is just a summary to make sure that everyone is familiar, because I'm going to use these concepts, right? Because especially for mobile phone, okay, you do the cross-compilation for Android. You need to use a tool chain from the NDK. I will provide some instructions. And the device where you are building the application, your laptop, is certainly not the same. So, what are the steps for building these applications? I have a few links, and maybe I will leave all the links for the analysis. So I'm going to actually change a bit the format that I had in mind, simply because it's not super easy for me to share the screen and go into the example. So what I'm going to do it, we're going to see all the use cases first, and we're going to do the support and technical material later all together, so I don't need to do back and forth. So for the Llama example, so in the executorch repository on GitHub, once you have cloned it, you need to basically install the executorch dependencies. There is a bash script, if I recall correctly, to install all the dependencies. And then you need to build the executorch static libraries, the core of executorch, in order to integrate these in your application. There is an official support for CMake. Then, in executorch, you already have the example for Llama, for running Llama 3.2 in particular. So you don't need to write an application to run Llama 3.2. So you just need to build the Llama example with an extra CMake provided for the Llama example, and just run it. If you are running locally on your laptop, I think once you have the binary, it's just a matter on the terminal to run the model, to run the binary, and to provide the model. In the tutorial, there are the steps that highlights how to convert the model and how to run it. Okay, so we skip for later. If you're not familiar with the Android NDK or the Android cross-compilation, this is very important, because the instructions you have here are the same for all projects, okay? So for all frameworks. Either you're using executorch, you're using LightRT with CMake, you're using llama.cpp with CMake, you're using whisper.cpp with CMake. When you cross-compile for Android, you need this, and that's it. So what you're going to do with these three flags in the CMake, you're basically telling the CMake where to look for the compiler or the toolchain that you need for cross-compiling for Android, And one specific API in this particular case is a CPU based on ARM, or targeting, for instance, an Android phone. And you just need to provide the Android platform. That's it. In order to use the toolchain, you need to download it from the official developer website from Google. And from there, basically, it's just a zip file that you need to uncompress and provide the path for that. So the path, just to make sure, will be this. Android NDK. This is an environment variable that will contain what you're going to unzip after you have downloaded the Android NDK. So we'll see later some documentations. Let's go to the second use case that I love it. I love it. This is something that I really hope you go home and you build your smart assistant to control your devices. Okay? So in the past, we're talking about a smart speaker and say, hey something. Hey. No, because if I'm going to say something, I'm going to trigger all your mobile phones for sure. So, hey, can you turn the light on? Or can you turn the TV off? What's the, how can I go to Milan? Or can you tell me a joke? Can you tell a story to my kid, Alice? Okay? Before, all of this was, well, just keyword spotting. We knew from TinyML, right? Keyword spotting, hey, detected locally. Everything else in the cloud. So the storing, the control of your lights, everything, all. Now with LLMs, we can do everything locally. There is no necessity to use internet connection. Or maybe the internet connection, the Wi-Fi, can be used to direct control your devices at home. So this device can be, let's say, tailored for specific use cases, right? We can tell stories. We can also tell the device who are the members of the family. Okay? Alice. Or, for instance, in this case, Orbit could know the name of my daughter. So, pipeline, what do we need? We need keyword spotting still on device. Speech to text, you convert the speech to text, for instance, using Whisper. You use LLM, I use a Llama 3.2, for instance. Why? Because it's quite small, it's 1 bit. I use also the text-to-speech. I'll give you an example with Piper. So these are the three things that you can run locally, everything, okay? In that particular case, I don't remember what was the LLM. But yes, you can use any LLMs, honestly. There is no... And you can also fine-tune it to also adjust the answer. So at least Milan is not the capital of Italy. So, I'm not sure if you're familiar with Whisper.cpp. Whisper is a model for speech to text, and Whisper.cpp is a very lightweight framework if you want to have an easy of use experience. Let's say I want to try it. Okay, I don't want to waste my time. So I can go to Hugging Face, download the Whisper models already converted for Whisper.cpp, and I think the build steps are CMake, make, run. I think that's it, more or less. And you have different data types supported for Whisper. You can run these models in integer 4 per block, integer 8, and many, many others. It runs on CPU, and all these examples that I'm showing, by the way, are tailored for the CPU, so that the reason is quite simple. I mean, I don't know what devices you have at home, all right? But for sure, you're going to have a device with a CPU, okay? So across all the devices, you can deploy these examples, including the Whisper.cpp. Here I have also reported the pre-trained models and the link to the project. So if you want to test speech to text, it's very straightforward. If you want to test Whisper.cpp on Android, don't forget about what I mentioned earlier about these steps. Okay. For Piper, this is another model. This is just an example. There are many, many other examples. Piper is a model for text-to-speech, which is optimized, as stated in the README of Piper, for Raspberry Pi 4. So it's quite very, very, for the edge, actually. So it's very, very edgy. So the model is in ONNX format. What did I say before? If it is in ONNX format, try to use the ONNX runtime. It's just easier, right? And here is I recommend the ONNX runtime. And also in this case, you can build it for the CPU. You don't need dependencies. It will simply run. Some info. So for building this type of application, for instance, the target frameworks can be Executorch, Whisper.cpp, and ONNX runtime. Executorch for instance, for running the LLM part, Whisper.cpp for running the speech text, and the Piper through ONNX runtime. So I recommend to try the Whisper Tiny, for instance, with the Inter4 with per block quantization. It's going to be quite small, but it works. It works quite very well. For sure, the speech to text there was running with integer 4 with per block quantization. Llama 3.2 is the same as before. Piper, what I recommend is the FP16 computation. Okay. The reason is simple. When we talk about audio, we love to use integer 1, but you need to generate samples. And samples are usually either in 16-bit, 32 bits, or also 64 bits. I mean, it's usually 16 and 32, but therefore, it's very difficult to use a fully quantized model. So my recommendation is, if you want an easy of use experience, don't waste your time. It will run well with FP16. Here, you need at least 5 gigabytes of RAM. So the target devices for the edge maybe is a Raspberry Pi 5. But again, it can run everywhere. It can run Linux, Android, Mac OS. That was on mobile from 2-3 years ago. Okay, so, and it's almost real time. Except, I mean, the answer was wrong, but you got anyway the idea. AudioGen. So AudioGen was presented for the first time at MWC 2025 this year. Stability AI. Do you know Stability AI, by the way? Who knows Stability AI? No? Stable Diffusion. Okay? Well, this is the company behind Stable Diffusion. So Stability AI is a company that they build very, very cool generative AI models for generating images, for generating 3D characters, including audio. And so we had this collaboration to demonstrate two things: the feasibility of running this model on the CPU, but also in a small amount of time. You can deploy a model. I mean, if you have infinite time, you can also deploy, well, we'll see in 6 months. We're going to do the quantization. So we wanted to demonstrate actually the feasibility of deploying these, let's say, in just a month, because we started, let's say, around January. And the demonstration was audio generation with no internet connectivity with stable audio open small, which is an open model officially released in May. It's on Hugging Face, and there is also a technical paper that we wrote together to detail all the technical aspects behind the model and the deployment on device. Let me see if I can, because you heard the example, right? Oh, it doesn't work. Maybe? No. No, it doesn't. No. I will. So it works. Let me see. I cannot give you the phone, otherwise you're gonna ask interesting questions. But let's say, for instance, you are editing a video on your phone, and you need a rain and thunder audio sample. You have two options. You either go on the website and you search for a rain and thunder audio sample to put in your video, or here you write it. It's processing. It should take roughly 6-7 seconds more or less. The quality is amazing. Here we are not talking about, well, it's interesting. This is 44 kilohertz audio sample generated on device with stereophonic effect. This is almost near what a professional music or video editor would like to have. Another example, a magic spell. Let's assume we have the magic wand from Pete Warden for Tiny Man, right? Let's see if I have something. Yeah, it works. So it's not just about music, it's also about sound effects. And if you have a mobile phone and you want to edit a video, you know that sometimes you need these effects. And you can just prompt it and it generates the audio. So how the model looks like. This is a very, no, it's not very high level. This is actually all the components of the model. The technology is very similar to Stable Diffusion, okay? What we have the prompt and the time as an input, okay? The time specifies how long I want the audio sample for. Usually is around 11 seconds. The prompt is the description of the audio sample you'd like to generate. Rain and thunder, or disco beats 120 BPM. You have the conditioner. The conditioner is the step that is used to embed your prompt to an high-dimensional space. And then you have the DIT, that is the diffusion part. That actually this is a component which is repeated several times. Okay, it is initialized with what? With a random value, and this is actually quite cool as a technology. So random initialization and iteratively, I think is 8 in the number of steps in the demo. It can work also with 4 steps. You're gonna probably sacrifice a bit of accuracy, but it will run much faster as well. You do it several times. Then you have the autoencoder. Well, remember, so you want an audio sample. So what they did, they also integrate the autoencoder, which is responsible to uncompress the data. Because what you have here as an input is like a compressed audio. What does the autoencoder basically uncompresses the data, and it generates the stereophonic audio sample that we heard earlier. So the DIT and autoencoder are very expensive. The autoencoder is probably the most expensive one. DIT is quite expensive. So the T5 is not crucial from a computation perspective. Therefore, the effort for optimizing this model was spent mainly on these two models. And here we're going to see in a bit the crucial role of mixed precision and also the role of floating point data types, that in some cases we have to use it. In Edge AI, we usually talk about integer quantization, but there are some use cases for generative AI in particular where the floating point arithmetic is needed. So stable audio OpenSmall, just to recap, generates 11 seconds of audio. The execution time, it depends on where you're running. If you're running on a laptop, it can run in probably 4 seconds or less. If you're running on mobile, it can take around 7 seconds. This is what we have seen. It can run on Raspberry Pi, but you need at least 5 gigabytes of RAM. The audio samples are absolutely good, very good. I'm not going to play this because we have already heard about. These are few examples of prompt. Well, you need a prompt engineer for this, but by the way. But this one is actually quite interesting. A tribal ambient plant flute is something that actually everyone can, even if you're not experienced. Rain and thunder, you don't need a prompt engineer. You just write it because I need my audio clip, and it generates that for you. We're going back to the beginning of this workshop. So for music creators, so this is the reason why we need this on device. It is an iterative process. It's not like, well, generate this song and I will be super happy. But because if it is like that, we're not going to have musicians anymore. Musician is a person that needs to find the inspiration, the right beat, the right samples, and to do it, it requires time and an iterative process. By doing this locally, we basically bypass the problem sending infinite requests to the cloud. This is crucial. It's crucial for who is deploying the model, because they need to consider an infrastructure to consider all the requests from users. I mean, try to imagine 1 billion people and they need at least, I don't know, more than 100 requests for generating the music. So it's going to be quite interesting. So it saves time and it saves also cost. But what data types for audio gen? We're approaching the end of this workshop. So we wanted to demonstrate the feasibility of running on the device, but we didn't want to demonstrate, well, you can run it, but to achieve that, you need to sacrifice sample rate, no stereophonic effect, because yes, one thing is demonstrating the technology, and one thing is demonstrating actually the full potential of a technology, right? And this is actually a demonstration of a real application on device. And I'm stressing this point because the quality is incredible. But in order to achieve this goal, we had to play with data types. And what we did, we applied the dynamic intake quantization per channel for the DIT. We tried also integer 4, but unfortunately it could not work. Either per block, per channel, it wasn't an option because the diffusion was accumulating the error. Remember, it's an iterative process. So if you have an error, you accumulate an error several times. The autoencoder is responsible for generating the audio sample, right? This is probably the most critical part. And we use FP16 in the demo. But in the paper, we also said, well, if you want, you can also quantize per layer some layers with integer 8. We haven't published the model because we wanted something that could run everywhere on all devices without problems. But something you could try is to do mix and match between int8 and FP16. FP16 for the critical layers and int8 for the other ones. And it's actually, if you're targeting the CPU, this is very, very simple because of the software programmability provided by the CPU, is straightforward. These are a few, as I mentioned earlier, these are a few figures about how long does it take to generate an audio. Around 7 seconds on mobile. On the laptop, it can take around 4 seconds. If you're using the quantized model, even less. Some information. What target framework did we use for this? We use LiteRT. So this is a demonstration. Actually, all the use cases we use different frameworks. This is using LiteRT. There is a README, the learning path. You just need CMake ... make -j whatever number process you want, 8, download the model, and that's it, and run it. In the tutorial, there are also the tutorial for converting the models from floating point to the integer quantization. Why this is important? It's important for audio gen, but if you're using LiteRT for the first time and you have a model and you want to convert it, I think this is an interesting place to look at, because there are some scripts that you can reuse also for the models you have on your end for Edge AI. Not necessarily generative AI, it can be any models you're targeting with LiteRT. Again, target devices, all CPUs. You don't need specific, you don't have limitation. The only limitations, again, but we're talking about GenAI, is about the RAM availability. The recommended RAM availability is around 5, although I usually recommend more than 5 because in particular this example, we haven't introduced an optimization at the memory level that we are planning to integrate anyway very, very soon. We have finished. Let's see if we have a bit of time, but I want to thank all these people because all these use cases that are publicly available, all the optimizations that we have landed in all these open source projects, in particular through the Clyde AI library. And if you're not familiar with Clyde AI, you can look at the website or ask me questions at the end of this workshop. It was possible because of all these people and many, many others. So in particular from ARM, all these people, and from Stability AI, in particular for the audio gen application, because it was a collaboration between ARM and Stability AI. I think with that, we just need to cut Milan, and we are done. Perfect. Thanks a lot for watching. It was absolutely a pleasure, and I hope to see you again.